Hi science students. In this video we're going to examine falling objects and the different forces that are acting on them. We also want to understand the effect of air resistance on these objects, in particular how air resistance seems to affect lighter objects more than heavier objects. Now I'm going to show you this video to begin with. So this is a video of Brian Cox, the famous scientist who does lots of documentaries on TV, visiting a vacuum chamber. And in this vacuum chamber, they're going to drop a bowling ball and a bunch of feathers. This is a really a common observation of ours, is that the bowling ball will fall to earth much more quickly than the feathers when air resistance is present. Now, this can be confusing because in physical sciences, we're taught that objects of different masses will fall to earth at the same rate. But when air resistance is involved, clearly they don't. However, later on they go ahead, here we go, and they evacuate all the air from this chamber, and they drop the bowling ball and the feathers. When there's no air resistance, no air in the chamber, they do fall at the same rate. So we're going to do some calculations to demonstrate how air resistance will affect lighter objects more than it does heavier objects. So let's close this up now, and just going to briefly talk about the forces acting on this cat, and then we'll do some calculations on a soccer ball and a bowling ball. Okay, so we've got a cat sitting on a chair. The forces acting are force due to gravity, Fg, which is equal to the mass of the cat multiplied by acceleration due to gravity. I'm going to say that this cat has a mass of 2 kilograms. So the weight force, or the force due to gravity of this cat, and sometimes you'll see this as Fw instead of Fg, is 2 times 9.81, which means it's 19.62 newtons downwards. Now clearly this cat is not falling through the chair, so there must be another force acting, and that force is this normal force. Now that normal force is equal in magnitude but opposite in direction to the force due to gravity, so it balances that out, meaning that the net force acting on the cat is 0. Alright, so in the next picture we have a cat falling through a vacuum. There's nothing for the cat to rest on. So in this case, the only force that is acting is the force due to gravity, 19.62 newtons downwards. If the cat is falling through air, then that force due to gravity is still there, but there'll also be some air resistance in the opposite direction to which the cat is moving, so it'll be upwards. So we can see that air resistance is important when objects are falling towards Earth through air. Let's have a look at the soccer ball and the bowling ball example and do some calculations to demonstrate that the bowling ball will accelerate towards Earth more quickly when air is present. Okay, so we've got a soccer ball. I'm going to say that the mass of the soccer ball is 1 kilogram. For the bowling ball, the mass is going to be 10 kilograms. These might not be exact to regulations for soccer balls and bowling balls, but I'll say they're close enough. So, when they're falling through air, the soccer ball will have force due to gravity downwards. So that is going to be, I'll just call it Fw for weight force, is mass 1 kilogram times acceleration due to gravity, 9.81. So 9.81 newtons downwards. 9.81 newtons that way. So for the bowling ball, the weight force is clearly going to be 10 times that amount because it has a mass 10 times more. So we'll make the arrow look bigger. So we've got 98.1 newtons downwards. Now these balls are both the same sort of shape and size, so I'm going to make an assumption that the air resistance is similar for both of these. I'll just switch to red for air resistance this time. I'm going to say air resistance on each of these is 1 newton. You know, that's not an unreasonable thing to assume because, like I said, they're a similar size and similar shape, so they would have a similar amount of air resistance to one another. Now what I want to do now is calculate the net force and hence the overall acceleration of these objects. So the net force for the soccer ball, now remember that's going to be made up of the weight force, Fw, and we add to that the air resistance. So Fw is 9.81 plus, now air resistance is in the opposite direction, so I'm going to say in this case that down is positive so we'll say air resistance being upwards is -1 because it's in the opposite direction. So the net force acting on the soccer ball is 8.81 newtons downwards. Okay, now for the bowling ball, the net force is equal to the weight force, which was 98.1, minus air resistance. So overall, 97.1 newtons downwards. So let's use these to calculate the acceleration of each object. So remember from Newton's second law that force equals mass times acceleration. So this means acceleration is equal to force divided by mass. Okay, so for the soccer ball, the acceleration, so soccer ball, the acceleration is equal to force, 8.81 divided by mass, which is 1 kilogram. So 8.81 meters per second squared downwards. For the bowling ball, acceleration is equal to 97.1 newtons over 10 kilograms, which is 9.71 newton. Sorry, not newtons. 9.71 meters per second squared downwards. So we can see that the rate of acceleration for the bowling ball is greater than the rate of acceleration for the soccer ball. The air resistance is similar for both, but because of that greater mass of the bowling ball, it has a greater ability to overcome that air resistance because its mass is so great compared to the force of air resistance. Now, if we were to look at these in a vacuum, the soccer ball and the bowling ball in a vacuum, remember now that there's no air resistance. So all we've got is, for the soccer ball, it was 9.81 newtons downwards due to its weight. And for the bowling ball, 98.1 newtons downwards. Now, acceleration equals force over mass. So for the soccer ball, the acceleration is the force, 9.81 over the mass, which is 1, so 9.81 meters per second squared. So you can see now that when there's no air resistance, the soccer ball is just accelerating towards Earth at 9.81 meters per second per second. For the bowling ball, the acceleration, 98.1 over 10, gives the same, 9.81 meters per second squared downwards. So when there's no air resistance, we demonstrate that the acceleration of each object is the same, and just acceleration due to gravity, 9.81 meters per second per second. However, when air resistance is involved, we can demonstrate that the heavier object has a greater acceleration, hence it falls to Earth more quickly. Okay guys, thanks for watching.